The Fairbanks-Morse trainmaster should have been unstoppable. It was the most powerful diesel locomotive of its era, capable of outpulling anything on American rails, and on paper it looked like the future of railroading. Instead, mechanics refused to work on it, crews walked off jobs, and shop foremen begged management to send the engines anywhere else. By 1963, the hatred was so complete that Fairbanks-Morse quit building locomotives forever. Here's how a submarine engine destroyed an entire company. Fairbanks-Morse started about as far from locomotives as a company could get. Erastus and Thaddeus Fairbanks founded the E&T Fairbanks Company in 1830 in St. Johnsbury, Vermont, and they built mechanical scales. For decades, they weighed everything from grain to cattle, building a reputation for precision and reliability that made them a household name across industrial America. They expanded into various industrial products over the years, including railroad equipment like baggage carts and ballast loaders, but engines were nowhere near their core business. By the early 20th century, Fairbanks-Morse had established a major plant in Beloit, Wisconsin, and ventured into engine production. They started with gasoline engines and moved to diesel in 1922, finding success in stationary power and marine applications where their engines proved reliable and efficient. The company licensed technology inspired by Germany's Junkers Umo 205 aircraft diesel in the 1930s and adapted it for American industrial use under the guidance of engineer Fritz P. Gruchner. The first prototype was a 6-cylinder model in 1933 with a chain-driven upper crankshaft, an unusual setup that would later evolve into something far more ambitious. By 1938, the engine had developed into the 38 D818, a design that would define everything Fairbanks-Morse attempted in the locomotive market. The numbers in the name told the story: 38 inches of cylinder height, an 8 1/8 inch bore, and configurations available from 4 to 12 cylinders, depending on the power requirements of the application. The engine found its true calling during World War II, powering United States Navy submarines, including the famous Gato, Below, and Tench classes, where its reliability in cool sea-level conditions proved invaluable for the war effort. When the war ended, Fairbanks-Morse faced a decision. They'd built massive production capacity for submarine engines, and peacetime meant that capacity would sit idle unless they found new markets. American railroads were rapidly replacing steam with diesel, creating enormous demand for new locomotives. The company saw an opportunity to use their proven submarine technology on the rails, taking advantage of wartime expertise to compete with established builders like EMD, Alco, and Baldwin. The logic seemed sound at the time. If the engine worked underwater in the most demanding military applications imaginable, it should certainly work on land pulling freight trains across the country. They were about to discover that submarines and railroads operate in very different worlds. The engine that Fairbanks-Morse brought to the locomotive market was unlike anything American railroads had ever seen. Most diesel engines have a piston at the bottom of a cylinder and a cylinder head at the top, with valves controlling the flow of air and exhaust gases. The Fairbanks-Morse opposed-piston design threw all of that away completely. Instead, it put 2 pistons inside the same cylinder, moving toward each other, with combustion happening in the space between them when they met. This arrangement eliminated cylinder heads entirely. Without a cylinder head, there was no place for valves, so the engine used ports in the cylinder walls instead of traditional valve mechanisms. As the pistons moved apart after combustion, they uncovered exhaust ports near the bottom and intake ports higher up in the cylinder liner. A Roots blower or turbo supercharger forced fresh air into the cylinder to push out the exhaust gases and fill the space for the next combustion cycle. The lower crankshaft led the upper by 12 degrees to ensure the exhaust ports opened first, giving burned gases time to escape before fresh air rushed in. 2 crankshafts meant twice the mechanical complexity of a conventional engine. A vertical drive shaft connected the upper and lower crankshafts through a gear train, synchronizing their motion so both pistons reached the combustion chamber at exactly the right moment. The timing had to be perfect every single cycle, and the components had to withstand enormous forces without losing alignment over thousands of operating hours. The design offered real advantages on paper that made engineers excited about its potential. With 2 pistons sharing each cylinder, the engine produced a power stroke with every crankshaft revolution rather than every other revolution like a 4-stroke diesel. Fewer moving parts theoretically meant fewer things that could break during operation. No cylinder heads meant no head gaskets to blow under pressure. The thermal efficiency was excellent because more of the combustion energy pushed the pistons rather than escaping through a hot cylinder head that conventional engines required. In submarine service, these advantages translated into reliable performance that the Navy valued highly. The engines ran at constant speeds, driving generators, with abundant cool seawater available for cooling and filtered air in controlled environments. Submarines didn't idle for hours in switching yards waiting for assignments. They didn't climb mountain grades in desert heat while pulling thousands of tons of freight. They didn't sit cold for days between runs and then gas to start immediately and work at full power. What worked beautifully underwater would prove to be a complete nightmare on land. Fairbanks-Morse delivered their first production locomotive to the Milwaukee Road on August 21, 1944. The H-1044 switcher carried a six-cylinder version of the 38 D8 1/8 engine, producing 1,000 horsepower, and it marked the beginning of a locomotive lineup that would eventually span switchers, road switchers, and cab units with power ratings from 1,000 to 2,400 horsepower. The company built locomotives through several partnerships and arrangements. General Electric's Erie plant handled cab units, and the Canadian Locomotive Company in Kingston, Ontario, produced models sold to Canadian railroads under designations like the CFA and CPA series. Raymond Loewy provided styling for several designs, giving Fairbanks-Morse locomotives a distinctive semi-streamlined appearance with slanted noses and tall hoods that accommodated the vertical opposed-piston engine that sat much higher than conventional diesels. Early sales seemed promising enough to justify continued investment. Railroads like Santa Fe, Baltimore and Ohio, New York Central, and Pennsylvania Railroad purchased units, attracted by the impressive power numbers and Fairbanks-Morse's wartime reputation for quality engineering. The company produced switchers like the H-1044 and H-1244 for yard duties, road switchers like the H-1644 and H-2044 for mixed service, and cab units including the Erie-built series that promised 2,000 horsepower for mainline freight and passenger operations. The flagship of the entire lineup arrived in 1953 with the H-2466 Trainmaster. This massive locomotive packed 2,400 horsepower from a 12-cylinder opposed-piston engine into a 6-axle frame, making it the most powerful single-engine diesel locomotive available anywhere in the world at the time. The Trainmaster could accelerate faster and pull harder than anything EMD or Alco offered, and it generated genuine excitement among railroad motive power officials who saw opportunities to reduce the number of locomotives needed for their heaviest trains. Between 1944 and 1963, Fairbanks-Morse produced approximately 1,500 locomotives total. That number sounds respectable until compared to EMD, which was selling thousands of units every single year to railroads across the continent. Fairbanks-Morse never captured more than a small piece of the market, and the reasons for that failure became painfully obvious as railroads accumulated real-world experience with the opposed piston design in daily service. The power was impressive. The problems were far worse. The hatred that railroads developed for Fairbanks-Morse locomotives centered on maintenance. Every diesel locomotive needs regular service to stay operational, but the opposed piston design demanded procedures so complex and time-consuming that shop crews came to dread seeing FM units roll through their doors for any kind of work. Replacing a power assembly on an EMD locomotive took about an hour with experienced mechanics. A skilled crew could pull the cylinder liner, piston, and connecting rod as a single unit, swap in a rebuilt assembly, and have the locomotive back in service before lunch. The modular design made maintenance predictable and fast, which meant locomotives spent more time earning revenue hauling freight and less time sitting in shops waiting for repairs. Replacing a power assembly on a Fairbanks-Morse locomotive required removing the upper crankshaft entirely. The process could take days rather than hours, and it demanded overhead cranes, precise alignments, and specialized knowledge that many railroad shops simply didn't possess. Wartime modifications made during submarine production had shortened certain components to fit tighter spaces underwater, which meant mechanics had to disassemble connecting rods through the top of the engine and remove pistons from the bottom, stocking variant parts and risking errors at every step of the complicated procedure. Railroad shop crews had been trained on conventional diesel engines, primarily EMD products that followed logical, standardized procedures developed for ease of maintenance. When Fairbanks-Morse units arrived, mechanics found themselves facing an entirely unfamiliar design that punished mistakes severely and offered no forgiveness for shortcuts. One mechanic described FM locomotives as requiring twice the machinery removal of other builders just to access bottom-end components that needed routine service. The frustration built until mechanics simply refused to work on the locomotives at all. Shop foremen reported crews walking off jobs when assigned to Fairbanks-Morse units, preferring disciplinary action to spending days fighting an engine design they considered dangerous and unnecessarily complicated. This wasn't laziness or stubbornness without cause. The opposed-piston layout genuinely required expertise that most shops didn't have and couldn't easily develop while still maintaining their regular fleet of conventional locomotives. When your own mechanics won't touch your product, you have a serious problem. Beyond the shop floor, Fairbanks-Morse locomotives suffered from reliability problems that railroads found completely unacceptable for revenue service. The issues emerged most severely in conditions that differed from the controlled submarine environments where the engine had originally proven itself. Overheating plagued the design in ways that conventional diesels simply didn't experience. The opposed-piston configuration lacked the cooling effect that incoming fuel-air mixtures provided to piston faces in four-stroke engines. In hot environments like desert operations, or when trailing units had to breathe exhaust-heated air from locomotives ahead of them, the lower pistons could overheat to the point of failure. Liner damage, piston seizures, and in some cases actual explosions resulted from thermal problems that the closed-loop cooling system couldn't adequately address without the abundant seawater that submarines enjoyed. High-altitude operations created additional stress that the design handled poorly. Western railroads like Union Pacific operated across mountain grades where thin air, temperature extremes, and heavy loads combined to push locomotives beyond their limits. The opposed-piston engine, rated at higher brake mean effective pressure for locomotives than it had been for naval service, simply couldn't handle the punishment that these conditions delivered day after day. Idling proved uniquely destructive to the opposed-piston design in ways that surprised everyone involved. When conventional diesels sat idling between assignments, they continued to lubricate and protect their internal components adequately. The Fairbanks-Morse engine suffered oil drainage from upper components during extended idle periods, which caused dry starts when the locomotive was called back to duty. Piston rings stuck from hardened oil residue, ports fouled with carbon buildup, condensation corroded internal surfaces that should have remained protected. Railroads reported rough running, excessive oil consumption, and seal failures after their FM units sat inactive for even moderate periods between runs. The locomotives performed acceptably only in specific circumstances that most American railroads couldn't provide. Southern Pacific found success using FM units in Bay Area commuter services where constant operation kept the engines warm and lubricated. But typical freight operations with variable loads, frequent stops, and periods of inactivity between assignments exposed every weakness the design possessed. An engine that only works under perfect conditions isn't much use to a railroad. Even when railroads wanted to keep their Fairbanks-Morse locomotives running, the company's small market share created support problems that made the effort nearly impossible to sustain over time. EMD dominated the American locomotive market with shares approaching 90% by the late 1950s. This dominance meant parts were available everywhere, mechanics were trained on EMD products by default, and service networks could respond quickly to any problem a railroad encountered. When an EMD locomotive needed a component, the part was probably in stock somewhere nearby. When it needed specialized attention, trained personnel could reach it within reasonable time. Fairbanks-Morse couldn't match any of this infrastructure with their tiny slice of the market. Parts shortages caused delays measured in weeks rather than hours. Locomotives sat waiting for components that had to be manufactured or shipped from distant warehouses that didn't stock items in the quantities railroads needed. Shop logs from the era show that fewer than half of trained master locomotives were serviceable on any given day, a utilization rate that made the high purchase price impossible to justify through operational savings. The company also relied on Westinghouse for electrical components rather than manufacturing them in-house, which created additional supply bottlenecks when those components failed or needed replacement. A hostile corporate takeover disrupted operations during a critical period and cost Fairbanks-Morse a planned 60-unit order from Illinois Central that could have helped establish better economies of scale for parts production and distribution. Railroads prioritized cost control and uptime above almost everything else in their motive power decisions. A locomotive that sat in the shop waiting for parts wasn't earning revenue, and every day of downtime represented money lost that the railroad could never recover. Faced with a choice between Fairbanks-Morse locomotives that promised impressive power but delivered unpredictable availability and EMD locomotives that offered adequate power with reliable support, the decision was obvious to nearly everyone who had to make it. You can build the most powerful locomotive in the world, but it's worthless if you can't keep it running. The H-2466 Trainmaster represented everything right and everything wrong with Fairbanks-Morse's approach to the locomotive market. At 2,400 horsepower from a single prime mover, it offered more power than any competitor could match when it debuted in 1953. Railroads that needed to move heavy tonnage over difficult terrain saw immediate appeal in a locomotive that could do the work of multiple smaller units. Southern Pacific, Pennsylvania Railroad, and several other major carriers purchased Trainmasters, hoping to revolutionize their operations with this unprecedented power. The locomotive delivered on its performance promises in many respects. It accelerated faster than anything else available, pulled harder on grades. It handled tonnage that would have required 2 EMD units working together to move. But the 12-cylinder opposed-piston engine amplified every maintenance and reliability problem that plagued smaller FM locomotives. More cylinders meant more components that could fail. Higher power output meant more thermal stress on parts already operating near their limits. The complexity that frustrated mechanics on 6-cylinder switchers became nearly overwhelming on the massive Trainmaster power plant. Railroads that had praised the Trainmaster's raw capability quickly reversed their opinions as maintenance costs mounted and availability rates plummeted. Southern Pacific found the locomotives temperamental in California's varied terrain, where coastal fog gave way to desert heat within a single operating district. The Long Island Railroad reported extensive service interruptions that disrupted commuter schedules and generated passenger complaints. Only 127 Trainmasters were ever built, a number that reflected both the locomotive's impressive specifications and its complete failure to meet practical operational requirements. The design was ahead of its time in power output, but hopelessly behind in reliability and serviceability. Railroads wanted the capability the Trainmaster promised, but they couldn't tolerate the problems it delivered along with that capability. Being the most powerful meant nothing when you couldn't stay out of the shop. The strangest part of the Fairbanks-Morse story involves what happened when the opposed piston design crossed the Iron Curtain. Soviet engineers reverse-engineered the 38 D8-1/8 after World War II and produced their own versions designated 2D100 and later 10D100. These engines powered thousands of TE3 and 2 TE10 series locomotives that hauled freight across the vast Soviet railroad network for decades without generating anything close to the hatred American railroads expressed. The difference came down to operating conditions and expectations. Soviet railroads ran their locomotives hard and continuously, exactly the way the opposed piston design preferred to operate. Long freight hauls across Siberian distances kept engines at constant load without the idling, starting and stopping that degraded the design so badly in American service. When Soviet locomotives needed maintenance, centralized shops with specialized equipment handled the work rather than expecting every local facility to possess opposed piston expertise. American railroads operated differently in almost every respect. Shorter runs, frequent terminal stops, variable loads, and diverse climate zones across operating territories exposed the opposed piston weakness that Soviet operations avoided. American shop practices assumed interchangeable parts, standardized procedures, and mechanics who could work on any locomotive brand without specialized training. The Fairbanks-Morse design violated all of these assumptions completely. The Soviet experience proved that the opposed piston engine could work reliably in the right circumstances. It also proved that American railroads represented exactly the wrong circumstances for the design to succeed. Fairbanks-Morse had built a specialized tool and tried to sell it as a general-purpose solution to customers who needed something else entirely. The same engine that failed in America succeeded in Russia because the operating conditions matched what the design actually needed. By the late 1950s, the accumulated hatred and poor sales had pushed Fairbanks-Morse toward an inevitable conclusion. EMD's GP9 and other models dominated the market with reliable performance, easy maintenance, and support networks that reached every corner of the country. Railroads that had tried Fairbanks-Morse products were either selling them off or sidelining them in favor of conventional power that their shops could actually maintain. The company stopped locomotive production in February 1959, though final deliveries of units already under construction continued until 1963. In total, Fairbanks-Morse had sold approximately 1,500 locomotives over nearly 2 decades of effort. a number that represented complete failure compared to competitors who sold that many units in a single year. The decision to exit locomotives allowed Fairbanks-Morse to refocus on markets where the opposed piston design actually made sense. Marine engines continued to use the technology successfully, and naval applications remained viable because submarines still provided the controlled conditions the design required. Today, the successor company, FM Defense, under Enpro Industries, continues producing opposed piston engines for naval and stationary applications where the design strengths align with operational requirements. The locomotive era left behind a handful of preserved examples in museums, including Santa Fe H-1244 No. 560, where visitors can see the unusual engine that generated so much frustration during its operating years. These survivors represent both Fairbanks-Morse's engineering ambition and the fundamental mismatch between that ambition and what American railroads actually needed from their motive power. Fairbanks-Morse built locomotives that could outperform anything else on American rails. Those same locomotives generated hatred so intense that an entire company abandoned the market rather than continue fighting it. The opposed piston engine worked perfectly in submarines and failed completely on railroads, proving that innovation only matters when it matches what customers actually need. Hit that like button and subscribe for more stories of machines that changed history and the ones that couldn't.